Chapter 5, Cold Water Systems, Part 6. Selecting cold water systems. So far we have looked at how water is collected, cleaned and distributed to houses and industry. We will now move on to look at the cold water systems we install in dwellings, their components, testing and maintenance. Each dwelling should have a wholesome, often called potable, meaning drinkable, water supply. A wholesome water supply. The most important place being at the kitchen sink. In most domestic premises, it is likely that people will drink water from most of the taps. This means that water to all taps should be connected to the main supply or come from a protected storage system. Drinking water should also be provided in convenient locations in offices and other buildings, especially where food is being eaten or prepared. Domestic systems of cold water supply. There are two basic systems of cold water used in domestic dwellings. Number one, the direct system of cold water. And number two, the indirect system of cold water. The direct system of cold water supply. With this system, all cold water taps are fed direct from the main supply. This means that all the taps are provided with a supply of drinking water. Storage is required only for supplying cold water to the hot water cylinder via a 150-litre cistern. A feed system will not be necessary if the hot water is supplied via an instantaneous hot water heater or a combi boiler. The direct system is the most commonly installed type of cold water system in domestic properties because its installation is cost effective and there is usually a relatively high pressure supply available. Pipe sizes for the direct system. Pipe size depends on the system design, but generally speaking, a 15mm rising main will be large enough to supply most cold water demands for a 3 to 4 bedroom house, with all cold water outlets being supplied in 15mm, including the bath. If a hot water storage vessel is to be installed, then a 28mm cold feed pipe is needed to the hot water storage vessel supplied for a 150-litre cold water feed cistern in the roof space. On larger installations, a 22mm rising main may be required, but this will depend on the water needs of the household. If a combination boiler or instantaneous water heater is installed, when a 50mm mains cold water supply should in most cases be sufficient depending on the supply pressure and flow rate. Table 5.3 Advantages and disadvantages of the direct system of cold water supply. Advantages: cheaper to install, drinking water at all fittings, less pipe work, less structural support required in roof space for cold water feed cistern, more suitable for instantaneous showers, hose taps and mixer fittings used in conjunction with a high pressure unvented hot water supply. Smaller pipe sizes may be used in most cases, and good pressure at all cold water outlets. Disadvantages of a direct system of cold water supply. At times of peak demand, the pressure may drop. If the mains are under repair, the property has no water. If there is a leak in the premises, there will be a great deal of damage due to the high pressure. It can be noisy. Greater risk of contamination to mains. Greater wear on the taps and valves. more problems with water hammer, greater risk of condensation buildup on the pipework, which can easily be mistaken for a leak. The indirect system of cold water supply. With this system of cold water supply, only the kitchen sink and the cold water storage system are fed directly from the mains cold water supply. The other appliances are fed indirectly via the cold water storage system in the roof space. A large amount of water will therefore need to be stored to supply both cold water and hot water to appliances and fittings from a minimum of 230 litres of water stored in the system. The system is designed to be used in low pressure water areas where the main supply pipework is not capable of supplying the full requirement of the system. This type of system also has a reserve of stored water for use in the event of a mains failure. The cistern should be installed in as high as possible to increase the system pressure. Pipe sizes for indirect systems. Pipe sizes for the indirect system. Pipe size depends on the system design, but generally speaking, a 15mm rise in cold water main will be large enough to supply most cold water demands for a 3 to 4 bedroom house. The kitchen sink should be supplied with water direct from the cold water main, and 15mm pipework is adequate for this. The cold water storage system can also be supplied via 15mm pipework. A cold water distribution pipe, 22mm minimum. Cold water distribution pipe, 22mm minimum, distributes cold water from the cistern to the wash basin, WC and bath. The bath should be supplied from 22mm pipework because of a lack of pressure, but all other appliances can effectively be supplied from 15mm pipework. A 28mm or 22mm minimum cold water feed pipe is needed to supply the hot water storage vessel. This system is ideal when mixing valves and taps require equal pressure and flow rate, as both hot and cold supplies are fed from the same source, this being the cold water storage system. Table 5.4 Advantages and disadvantages of the indirect system of cold water supply. Advantages: reduces risk of water hammer and noise. Constant low pressure supply reduces the risk and rate of leakage. Suitable for supply to mixer fittings or for vented hot water supply. Reserve supply of water available in case of mains failure. Less risk of backflow, fewer fittings supplied directly. Showers may be supplied at equal head of pressure. Reduces demand on main at peak periods. Can be sized to give greater flow rate. Disadvantages: supply pipe must be protected against backflow from cistern. Risk of frost damage in roof space. Structural support is needed for cistern. Space taken up. Increased cost of installation. Reduced pressure at terminal fittings. Cold water systems in larger dwellings and high-rise properties. For larger buildings, office blocks, factories, hotels, etc., it is preferable for all water except drinking water to be supplied indirectly via a protected storage cistern or cisterns. Key term: multi-story, a tall building that requires boosting or pumping of the water supply pressure given its height. Cold water supply systems in multi-story buildings. In plumbing systems, The term multi-story applies to buildings that are simply too tall to be supplied totally using the pressure from the water main. Because of their design, these buildings have particular cold water system requirements that can be satisfied only by pumping or boosting the cold water supply either in part or in total. Most cold water supplies that are delivered from the mains cold water supply arrive at a building at 3 to 7 bar pressure, 30 to 70 meters head. A 30-meter head is equivalent to around 8 stories in height. When taking into account two-story margin to allow for frictional losses, it becomes obvious that the height of the building will often outstrip the head of pressure available. In some parts of the UK, it is not unusual to find premises with pressures lower than 2 bars and flow rates of below 15 litres a minute. In these cases, the water undertaker should be consulted as to where supply pressure can be relied upon to ensure the correct operation of the cold water system. If the public supply is inadequate or the building too high, then the water supply within the building must be boosted. There are several ways that this can be achieved, and these can be divided into direct boosting systems, direct from the cold water main supply, and indirect boosting systems from a brake system. Indirect systems are the most common, as direct boosting systems are often forbidden by water undertakers because they can reduce the mains pressure available to other customers in the locality and can increase the risk of contamination by backflow. However, where insufficient water pressure exists and the demand is below 0.2 litres per second, then drinking water may be boosted directly from the supply pipe, provided that the water undertaker agrees. With indirect systems, a series of float switches in the brake system starts and stops the pump's demanding upon the water levels in the system. Boosting pumps can create excessive aeration of the water, which, although causing no deterioration of water quality, can cause concern to the customer because of the opaque, milky appearance of the water. There are several common examples of these systems. Direct boosting systems, direct boosting to a drinking water header and duplicate storage systems, indirect boosting to a storage system, indirect boosting with a pressure vessel, direct boosting systems. Direct boosting systems, where permission from the water undertaker has been granted, pumps can be directly fitted to the incoming supply pipe to enable the head of pressure to be increased. A floating switch or some other no less effective device situated inside the high-level system controls the pumps. The pumps either switch on or off depending upon the water level in the system. The pumps are activated when the water drops to a depth normally equal to about half the system capacity, and switch off again when the water level reaches a depth approximately 50 millimeters below the shutoff level of the float operated valve. If the system is to be used for drinking water, then it must be of the protected type. Direct boosting to a drinking water header and duplicate storage systems. Direct boosting to a drinking water header and duplicate storage systems. This system is used mainly for large and multi-story installations. With this system, the cisterns at the high level are for supplying non-drinking water only. A drinking water header sited on the boosted supply pipe provides limited storage of 5 to 7 litres of drinking water to sinks in each dwelling when the pump is not running. Excessive pressure should be avoided, as this can lead to an increase in the wastage of the water at the sink taps, along with the nuisance of excessive splashing. A pipeline switch on the header bypass starts the pumps when the water level falls to a predetermined level. The pumps can be time controlled for activated to shut down by a pressure switch. When filling the cisterns, the pump should shut down when the water levels in the system are approximately 50 millimeters below the shutoff level of the float-operated valve. Secondary backflow devices may be required at the drinking water outlets on each floor. Indirect boosting to a storage system. Indirect boosting to a storage system. This system incorporates a brake system to store the water before it is pumped via a boosting pump, known as a booster set, to a storage system at a high level. The pumps should be fitted to the outlet of the brake system. The capacity of the brake system needs careful consideration and will depend upon the total water storage requirements and the system's location within the building, but it should not be less than 15 minutes of the pump's maximum output. However, the system must not be oversized, as this may result in water stagnation within the system. The water level in the storage system, or cisterns, is usually controlled by means of water level switches and control the pumps. Water level switches that control the pumps. When the water drops to a predetermined level, the pumps start to fill the storage cisterns. The pumps are then switched off when the water level reaches a point about 50 millimeters from the shutoff level of the float-operated valve. A water level switch should also be positioned in the brake system to automatically shut off the pumps if the water level drops to within 225 millimeters of the suction connection near the bottom of the brake system. This is simply to ensure the pumps do not run dry. Indirect boosting with a pressure vessel. Indirect boosting with a pressure vessel. This is a rather complicated system. This rather complicated system is used mainly in buildings where a number of storage systems are fed at various floor levels, making it impractical to control pumps by water level switches. In utilities, a pneumatic pressure vessel to maintain the pressure boost to the higher levels of the building. The pneumatic pressure vessel comprises a small water reservoir with a cushion of compressed air. The water pumps and the compressed air operate intermittently. The pumps replenish the water level and the pressure vessel maintains the system pressure. Since the system may be supplying drinking water, the vessel capacity is purposely kept low to ensure a rapid and regular turnover of water. The compressed air must be filtered to ensure that dust and insects are eliminated. Normally, the controls, including the pressure vessel, pumps air. Normally, the controls, including the pressure vessel, pump, air compressor, and control equipment, are purchased as a package, although self-assembly booster sets are available. As can be seen from figure 5.3.1, some of the floors below the limit of the mains cold water supply pressure are supplied unboosted direct from the cold water main, with the floors above the mains pressure limit being supplied via a brake system and booster set. Drinking water supplies must be from a protected system. Summary of cold water systems. In some cases, a combination of both methods of supply may be the best arrangement. In a dwelling or a house, for example, the ground floor outlets and any outside tap could be supplied under mains pressure, while all other cold water outlet fittings could be fed from a storage system. The performance of any cold water system is dependent upon the pressure of the incoming supply and its flow rate. Direct systems require a good pressure and flow rate because all of the appliances use mains cold water supply, and in some cases mains fed instantaneous hot water supply too. Indirect cold water systems where low pressure supply is used must be pipe sized correctly to ensure that the system meets the design specifications, as the lack of pressure is compensated for by an increase in pipe size and therefore flow rate.